Okay, good morning everybody. I hope everyone's having a wonderful day. So today we're going to be talking more about graphs, and depending on how far along we get, we're going to start talking about some algorithms that we can use to do things with graphs. So just as some reminders, the midterm is this Friday. It will be scheduled during class time. So as I mentioned the other day, there will be some 10-minute padding on the beginning and end. But it will be timed. It's a 50-minute midterm. Take a look at the format post I have on the course website. I went into quite a bit of detail there, explaining what kind of problems there are, what things you don't have to worry about, what the mark breakdown of each problem will be. And another thing is that I did add a couple of small things there that were based on a couple of questions I got during class time last time that I asked the IT people. I'm going to be meeting with them tomorrow for any last other details. So look at this format if you get a chance. And I also put up that mock test that I promised. So this is just for fun. It's not worth marks or anything. It's just to get you familiar with the kinds of problems that you should expect on this test in terms of what they look like. So for example, there's a true or false there. There's a multiple choice. And then there's this drawing example where you're going to draw me a fun picture. I already seen some pretty fun pictures that people have made for me. But yeah. Just remember, when you're drawing these pictures, make sure you click Save Picture and make sure it's drawn in the canvas area. The last thing you want to do is have it so like your picture's like slightly off to the left or the right. Because what will happen is I won't be able to see the whole picture, and that means I can't really grade your response the way maybe you intended. So make sure you review that carefully. So when you're drawing it, make sure you draw it in the space they provide. It's very tempting to kind of keep drawing in one direction. But yeah, so take a look at the mock test. It is set up for proctoring. So if you want to see what this proctor track will look like with the midterm, I did set it up also for 50 minutes, although you should not need that at all. I just kind of walk you through some tips just generally for approaching the problems for the midterm. So I recommend you try that out. Also, as a remark, I did open up the onboarding. Now it's open until the rest of the term. So if you ever find yourself needing to use the onboarding to get onboarded with, say, if you switch a computer or you're needing to do something like that, it is all set up for that. So don't worry. They will be open for the remainder of the term. Wonderful, wonderful. Okay. So as I mentioned before we got started here, assignment 3 is out. It will be due by the end of October 31st. The 8:30 rule still applies for the following morning. And I thought it would be kind of fun to make it on Halloween for the due date. You know, boo, I got to spook you, see. But anyways, it isn't, I assure you, and it isn't going to be that long of an assignment, but it is to just make sure that you can implement one of the data structures that we've seen in class. This one's based on priority queues and heaps. So hope you enjoy the scenario. I had a little bit of fun with this. But yeah, no, so just carefully read the specifications, just carefully. I went into quite a bit of detail there. But if you have any questions or anything like that, just don't hesitate to reach out to me about it. I think it's rather thorough, so when you open it up, it looks kind of lengthy. It's not actually that bad. So don't worry. It's just I have to be thorough. That way, when I communicate the specifications to you, what you need to do, because you're going to be implementing one class for me, in C++, and that's all you had to do for the assignment. This week, at some point, I will be giving you a test file, and this will be the same one that the TAs and myself would be using for grading your assignment. So you'll be able to actually try out a bunch of tests on your so-called batch class. So when that comes out, I will put out an announcement, okay? So other than that, as promised, assignment 2 sample solution is out, so you can take a look at that. But yeah, that's all my reminders. Are there any questions or concerns about that before we get started? Okay. Okay, I think so. Most people are good. Just one quick question. What will the course like till today? So today I'm going to be covering more about graphs, but the midterm, if you're asking about the midterm it's from the beginning of the course until the end of splay trees. Yeah, so the very last topic that will be on this test is splay trees. So that's the cutoff point. Okay, so if that's the case, no worries, no worries. So today we're going to be talking a bit more about graphs. Actually, it's all going to be about graphs. I love graphs. I hope I'm going to endow some enjoyment about graphs if you haven't seen these before. So I got to first talk a little bit about a few things, and then we're going to start talking about how we can represent graphs on computers, and also how we can, of course, do things with graphs. So first, I just want to give you just a little heads up about some terminology I'm going to be using. I will have more details about these things in the notes, so some of these things I'm going to say them, but I won't necessarily write them. So I encourage you to take a look at the course notes after class. So just a few things. So whenever we explore a graph, sometimes people call this traversing a graph. We often need some terminology to describe how we're doing this. Now, there's many different ways to describe several kinds of these so-called traversals of a graph. You may be familiar with tree traversals, for example. Like in-order traversal, pre-order traversal, post-order traversal. Traversal just generally means explore. So I need some language to help me describe how this happens. So the first thing I'm going to define is something called a path, which is just a sequence of adjacent vertices. So what I mean by that is I just simply, say for example, I go from, say if I start at V7, and then I go to, I'm going to go to V2, and then say I want to go to V3, and maybe I want to go to V4, and maybe I want to go to V1. Who knows, maybe I want to go back to V7, and then maybe I want to go to V6. This is a description of a path. Now, I must warn you that in the computer science community, typically people will use the path to talk about something called a simple path. So a simple path simply means that the vertices in the path are distinct. So all I do is I follow adjacent vertices. So my example here, the path would consist of vertices V7, V2, V3, V4, V5, and then I go to V1, and then I went to V7, and then I went to V6. So I could give them to you as a list of vertices, or I can give them as a list of edges. I must stress this, is that somebody can give them in either form, and that will that's a valid way of representing a path. Now, as I mentioned, a simple path is simply a path where all the vertices are distinct. So a question for you. Is this a simple path, the one I just described here? Can somebody tell me yes or no? No, right? No, of course not. Of course not. I revisited V7 here. This is not simple. However, here's an example of a simple path. I could say I could start it at V7. I don't necessarily have to start at V7. I'm just picking any one of these nodes or vertices. So I go V7, then the V1, and then the V5. Here's another path. Say V7, V1, V5. This is indeed a simple path because notice that I don't repeat any vertices. Now, some people in the graph theory community would simply say that what I'm calling a path, some people call this a walk, just out of. And then some people refer to a simple path as just a path. So just be aware that different people use different terminology for the same thing sometimes. So just be warned. So when I use the word path, I'm just taking some walk in the graph. A simple path is one where the vertices are unique. And as a consequence of this, all the edges in the path are unique as well. So you can actually take this terminology and you can kind of extend this a little further. So you can take these in combination with one another. So you can have a simple path, you may just have a path. But if I give you a directed graph, we have a thing called a directed path. This is where I just simply follow the arrows of my arcs or directed edges. And I can only follow in that direction. So if I give you some path, I have to follow in the same direction throughout my entire path. So the easy way I like to describe it is just follow the arrows. You're not allowed to go backwards. So if the arrow is pointing this way, you can't go this way across that arc. You have to follow the arrow. That's the main difference between these two, and we call that a directed path. And you could also have a simple directed path, because you can obviously just say, hey, look, are all the vertices unique or not? That's distinguishing. And lastly, one very important one is that sometimes we want to describe a path for which there's something called a cycle. So just as an example, say, for example, I go for a little trip with my blue marker here. This one does smell like blueberries. Ah, it smells like blueberries. I don't recommend doing this with normal whiteboard markers. Please don't do it. I don't recommend it. It does really smell like blueberries, though. I've had this marker surprisingly for years now, and it still works. So say, for example, I go to V7, then to V6, then to V5, then to V1, and then back to V7. So it's an example, of course, of a path, right? So I can go V7, then V6, then V5, then V1, then V7. Now I'd like some simple way to describe a path for which the place I started and the place I ended are the same vertex. This is what we call a cycle. So this is an example of a cycle. And likewise, you can have a simple cycle. That's where all the vertices in the cycle are distinct. So, for example, is this a simple cycle? Can somebody tell me yes or no? Excellent, excellent, thank you. Yeah, it's also a simple cycle because notice that all the vertices are unique. Sometimes this little change in the terminology does matter when you're describing things. Yeah. Now you might ask, how do I know that how can it possibly be simple? So now this is where you get around it in the graph theory terminology. So the first and the last one are allowed to be the same. So when I say a simple cycle, I'm basically taking both this definition here in conjunction with this one. So they have to be distinct, but the first and last ones are allowed to be the same. So it's both of them at the exact same time. So that's what I mean. So basically, I'm leaving the exception for the first and the end. So I basically ignore the last two and the first one. That's how I define simple in the context of a cycle. That's a wonderful question, by the way. So when I look at a cycle, I don't really care about the first and the last here. I just care that all of them, if I count each one of these, all of them have to be distinct. That's a wonderful question. So, that being said, are we okay with paths and cycles? Give me a thumbs up. Are we good with paths and cycles? So they're just a way of describing how I can explore a graph. So sometimes I would like to have some way of saying, can I go from this vertex to that vertex? Well, that would mean that there has to be some pathway, right? Yeah, if not, I have another example in the notes. So if you want to see another example, there's another one in the notes. So next I want to talk about a whole bunch of other terminology. So I'm going to kind of shotgun blast these. Not literally, of course, figuratively. I'm going to talk about a variety of different things, and then we're going to talk about how we can represent graphs on computers. So, like I said, I'm going to be blasting through a whole bunch of fun terms. So trees, forests, subgraphs, and connectivity. So I got to tell you what it means for a graph to be connected. So that's the first thing I need to do. So if I tell you a graph is connected, then what I'm saying is a graph is connected. A graph is connected if there exists a path from each vertex to every other vertex. That's as simple as the definition can be. So if I'm talking about connectivity, the first one is that I want to have a notion of a graph being connected or not. So all it says is if I look at any two vertices in my graph, so for example, this graph here. By the way, if you're curious about some fun graph theory, this is an example of what we call a wheel graph. We call it a wheel graph because you know this is like the spoke of the wheel, and then we have the outer perimeter. So you can look at it like a wheel that turns, like this. But a question for you, is this graph connected? So just remember, the way you check this is I just take any two vertices and I ask, is there a path from that vertex to this vertex? And I do this for all pairs of vertices. So in this example, the great thing is that it is indeed connected. I can find you any one path that gets you from one vertex in the graph to any other vertex. It's nice and easy that way. So if you're wondering, this is the definition commonly used for undirected graphs. So this is for, so when I talked about this, this is for undirected graphs. For digraphs, there are two kinds. So there's two notions of connectedness in a directed graph. I'm going to let you take a look in the notes for this, so just please see the notes. I have an example of showing you how this works, so see the notes for this. So there's two notions. There's what they call weakly connected and strongly connected. In weakly connected, so if I give you a directed graph, what you do is you ignore all the arrows on the edges. You just treat them like undirected edges. And then you ask the same definition right here. So is there a path from any vertex to any other vertex? So this is what in a directed graph we call weakly connected. Strongly connected is the other notion. So there's kind of two notions of connected in a directed graph. Strongly connected is where you literally take all the directed edges and you literally ask, is there a directed path from any one to any pair of vertices in the graph? So it must be stressed that just being strongly connected, that is actually a much stronger condition than just weakly connected, because weakly connected, I just ignore all the directions on the arcs or directed edges. So I'll let you take a peek at that. We're going to carry more about this definition right here. Now, another thing I need to talk about are trees. Now, I know that you've had trees and many trees and more trees and I don't know, even trees for breakfast. I don't know. But the point is that you've seen a lot of stuff about trees before, including in this class. So let's talk about trees. So a tree, it has a very simple definition in terms of graph theory. It goes like this. A connected, undirected graph that has m equals n minus 1 edges. So that's one way you could define a tree. Now you might ask, Dan, isn't that the tree property we talked about at some point earlier on in the course? And the answer is yes, that is the exact same one and you'd prove it the exact same way. So that's a way you can define what a tree is. Now, the twist here is that there's many different ways of actually characterizing what a tree is. So things are going to get a little funky here. If you don't like this definition, there's actually other equivalent definitions of what a tree is. So here is another equivalent way of defining what a tree is. Any two vertices in G are connected, are connected connected by a unique simple path. So that just simply means if I pick any two vertices in the graph, there has to be one unique path that takes me from that vertex to the other vertex. So the uniqueness is the important part here. So when I'm doing this, for example, this clearly isn't a tree, right? But notice if I ignore the outer, so this is actually a neat property about wheel graphs, by the way, is that you can ignore, if you ignore the outer perimeter of my graph, so all the edges that go around the outside, what does it look like? It looks like a tree. It's actually a tree. So if you were to ignore all the outer perimeter parts, you'll notice here that if I take this vertex and say, that vertex, a unique path to get me from here to there, there's only one. It's just from here to there. That's just an example. But I felt like I wanted to throw some fun graph theory at you. But you don't have to know about the wheel graph, just to be clear. This is just a fun aside. There's a lot of these fun graph structures that do exist out there. So here's another one. G is connected. G is connected, but if any edge is removed, so if any edge is removed, this is, I haven't defined this, but I'm just going to give it to you. The induced graph. So induced just simply means as a result of this operation. Is not connected. So what does this mean? If I go back to my wheel graph, say for example, like if I explicitly were to get rid of all of these, just to be clear that this is in fact a tree. So now look, the result is a tree. If I go back to my example I had before, remember, if I have it so that I can remove any one edge, you'll notice that I no longer have a path from one vertex to every other. That's a characteristic of a tree. So for example, if I get rid of this edge right here, say the one from V1 to V2 here, notice that there is no way I can reach V2, right? So this is another way you can define what a tree is. So G is connected, but if any edge is removed, the induced graph is not connected. Okay. And I must stress it's if any one edge. If any one edge. So this is a much stronger property than just I remove a certain edge. It's any one edge. Just to be very clear. Because it can give you all sorts of graphs where I can remove an edge and then suddenly it's not connected. It's that it has to be that I can take any one of the edges in this graph and now it's all of a sudden not connected. It has to be true for any edge I remove from this graph. Okay, another one is G is acyclic. So if you're not sure what acyclic means, it has no cycles. And the number of edges is equal to n minus 1. So that's another way you could define a tree, is that it has no cycles in it. And one last one. I have to do this to you because trees are fascinating, but you have to be aware that there's many ways you can define the tree. G is acyclic, but if any new edge is added, the induced graph has a cycle. So notice that in my example over here, if I just add any edge anywhere, notice now there's a cycle. I can go V1, V2, V3, V1. That's another way you can characterize what a tree is. So you can actually, there are more than just these, but I feel like I wanted to show you some. And the way you naturally prove these types of properties is you use one definition to help you prove another one. So isn't that neat? So there's a lot of different ways you can actually talk about what a tree is. I just felt like showing you a bunch of different ways I can do that. Sorry, I'm just clanging around over here. My apologies. Okay. So another thing I need to define for you is a forest. And it's a really simple definition. So it is a set or collection of trees. So it's just a whole, the name sounds rather straightforward, right? So for example, if I were to draw this, that's a tree. This is a tree. Say if I were to, so notice now I have technically 3 trees here. Just one node or vertex. Then I have this tree right here, and then I have another tree. And I must stress that for any forest, we know that m, the number of edges, is at most n minus 1, where n is the number of vertices. So notice it's not a strict equality, it's now an inequality. That's because the graph technically doesn't have to be connected anymore. Another notion I need you to be aware of is something called subgraph. Its definition is also rather straightforward, which is nice. It is just a subset of vertices and edges. Vertices and edges. A subset of vertices and edges that forms a graph H. So the key thing here is that I could pick some subset of the vertices and edges. So I just grab some of them. And if it forms a graph, that's a subgraph. So that's the most important part. You can't just like take an edge and then just not take its endpoints. It has to consist of both its endpoints if you include that edge in the subgraph, right? That's that most important part. It has to form a graph. So just as an example, promise this is going to be a more fun-looking graph. You may know what this graph is called if you've studied a little bit of graph theory. Not, I encourage you to there's actually a couple different ones actually quite related to this one, but I'm just going to draw a fun picture for you. So here's an example of a graph. And no, I'm not trying to summon the occult here. It's not that kind of Monday. The point here is that what I can do is I can take this the thing that looks like a star that people used to doodle all the time in school. I'm going to take that part of the graph. So for example, a subgraph here, say if I want to have H, and a way I can get H is just by taking I can take the vertices here. So for example, that's H. And the original graph is the stuff in black. So that's what a subgraph is. Some reason I put the blue lid on there. That's kind of funny. Anyways, are we okay with the definition of a subgraph? It sounds like a fun way to go into a Monday afternoon. Yeah. But don't worry, we're all doing good, I think. If something goes bad, you could blame me for it, okay? Hey, so I have only one other definition here. It is something called a connected component. And I know usually students, that first time they hear the definition, it's a little hard to swallow at first, because it sounds like a lot of jargon. So all a connected component is a maximally connected subgraph. So I must stress that when a graph is connected, it consists of all, so if a graph is connected, it has all the vertices so that there's paths that go between any two vertices. There exists a pathway. That's what it means to be connected. Now, what happens when you don't have a way to reach a vertex? Well, there's a possibility of including edges or not including edges in subgraphs. So what I mean maximally connected, that means that I'm going to include as many edges as possible in each one of the subgraphs so that it still is a connected graph. So just to give you an example of what I mean by this. So if I look at the graph itself, I want to take each part of the graph as a subgraph, and I want to have as many edges as possible in each respective subgraph. And we call each of the subgraphs a connected component. So here's an example of a graph overall. Here's an example. So what I would tell you is that this has 3 connected components. If I look at this subgraph, namely I take these 4 vertices, notice that among these 4 vertices, this subgraph is connected, right? There's a pathway I could go from here to there, and so on. I could do all the different combinations of doing this. I could do that for each one of these. So when I say maximally connected, I'm saying include as many of the edges as possible in your subgraph such that it's connected. So for example, if I were to, say, consider the subgraph of this part of the graph, say if I take this and I don't include this edge right here, this would be an example of something that isn't a connected component because it has to be as many edges as possible so that I have a connected subgraph. So just as so the easiest way you can think about this, a connected component, is you imagine it like, what are all the pieces of my graph such that each piece is connected? So for example, a connected graph, like I said before, a connected graph has one connected component. It's just the graph itself. If it, say, for example, actually this forest picture I have here, how many connected components do we have here? We have 1, 2, and 3. So this is an example of a forest, which happens to be, in our case, a graph with 3 connected components. But yeah, are there any questions about a connected component? So remember, when I say maximally, I'm saying as many edges as possible, such that if you were to remove an edge, now you'll notice that I can have paths from any 2 vertices, but you'll notice that I want it to be as many as possible. Okay, so if we're good with this, let me start talking about how we could represent a graph on a computer. So I'm going to show you 2 different ways of representing a graph. So I'm going to go a little bit over this, a little bit more high level. So questions asking, wouldn't you need the cross sections then? So when it comes about the connected components, so the one thing it's worth noting is that, like I said, you can't break it into pieces. So normally when people will study things like connected components, what they do is they'll try to exhaustively explore the graph as much as possible. And that's in fact actually how you get connected components. It's a very simple way of computing them. But yeah, I'm not sure what you mean exactly by cross sections, but you're welcome to ask me about it after. Remember, the graphs don't really have any geometric meaning at this stage. So I want to give you a picture just to accommodate into what I'm doing over here. So here's a picture I want to use. So I'm going to draw a graph. So I'm going to include 5 vertices in my graph. So I'm going to have V0 up at the top here. I'm going to have V4 that's going to have a path, an edge that's going to be incident on V0 and V4. I'm going to label its edge A just for simplicity's sake. there's going to be, on B, there's going to be two endpoints. There's going to be V3 and V4. On edge E, I'm going to have V1 and V3 as the endpoints. On edge D, I'm going to have V2 and V1 as the endpoints, and I'm going to have the last edge be labeled C. So we're going to be using this as an example to help us talk about how we could represent a graph. So I'm going to be showing you two standard ways of doing this, but there actually exist more ways of representing graphs that in different applications do actually have their own purposes. I'm going to be highlighting these two because they're very common in practice, but also at the same time, they're very useful when we talk about the algorithms we're going to talk about. So the first one I want to talk about is so-called the adjacency matrix. So you might ask, Dan, why can't we just encode the information of the graph in terms of asking if two vertices are adjacent to one another? And that's the idea of an adjacency matrix. So there's a couple of ways you can go about representing the graph using an adjacency matrix. I'm going to first describe the classic way, and then I'll give you the more generalized way, if you like a more OO-based way of looking at this. So each element in my two-dimensional array, or you can think of it as a matrix. It's typically thought as a matrix, but when you're implementing, it'll be a two-dimensional array or something that's the equivalent of this. So each one of the elements in A refers to if two vertices are in fact adjacent. So if I look at Aij in my two-dimensional array, if I see a 1, that means that there's an edge from I to j in the graph. So it just means I and j is in the set of edges. And if I see a 0, that means that there is no edge that has endpoints that are both I and j. That means they're not adjacent to one another. So this is the classic way you can approach encoding an adjacency matrix. And I've taken this picture here, and this is way you can represent that graph over there as an adjacency matrix using 1s and 0s. So just to be clear, when you're using an adjacency matrix, classically speaking, you have to have some way of labeling all the vertices so that they're numbers that you can index in your two-dimensional array. So very often you'll have some way of relabeling the vertices from 0 to n-1, where n is the number of vertices. So just as a quick example, if I look at, say, the row for V0, which is going to correspond to, so if you're wondering, each one of these, so if I have V0, this is V1, this is V2, this is V3, and this is V4. So I'm just using the subscripts, if you're curious. So if I look at the row for V0, you'll notice that the only entry with a 1 in it is the one that lies in the column for vertex 4. So you look at where the two meet in the matrix, and you say, oh, look, if it's 1, that means that there's an edge that takes me from V0 to V4 and vice versa. At least in the context of an undirected graph. I'm going to mention one small remark about this, but if I want to go from V0 to V4, I can just check this and say, hey, look, there's an edge right there. That means I can go to V4 or vertex 4. Likewise, I can look at, say, right here. Say if I look right here in the row for V2, if I look at column 1, when I see a 1 right here, that means that there is an edge for which the endpoints are V2 and V1. It's right here. So does everybody get the idea? So it's just a two-dimensional array. You encode 1s for whenever there's two vertices that are adjacent to one another. Sorry, I'm getting really excited here. One another, or it's 0 when they're not adjacent. Now, this is a classic way of doing it. It's a very simple but effective way of representing a graph using this matrix-based approach. There's a lot of ways you can interpret these matrices. For example, for those that like the linear algebra, for example, you may look at this matrix and you might ask, Dan, is this matrix symmetric? That means that if you take the upper triangle and you look at the lower triangle, are they the same? In any undirected graph, it actually is the case that they're actually symmetric. It's always a symmetric matrix. In directed graphs, you can use this to represent a directed graph, of course, but you may not necessarily have it where the graph is symmetric anymore. That's because in a directed graph, the way you'll interpret this will be, okay, is there an edge from a vertex to another vertex? So when you interpret a row and a column, they're going to be a bit different. Now, one thing that you can do as well, and this is one that if you like doing a lot of OO-based programming, this is a nice way of going about it. I wrote nil as an abbreviation, or for those that like using the word nil instead of null. Instead, you could use a more OO-based approach where whenever there is no adjacent vertex, you just put null in. So you put a null reference in, and whenever you have an adjacency, you can actually put an edge a reference to an edge object right here. So what you do is you can actually store the references to edge objects in the matrix. So this is another way you can approach it. So that's more of the OO-based. This is the more classic one. So that's just really what I mean when we talk about an adjacency matrix. So are there any questions about the idea of the adjacency matrix? So this graph corresponds to either of those. So I want to mention some pros and cons of each of these. Yes, what's up? Excellent question. So you'll notice that if I look at it like a 2D array, like this, so if you think of I, then J, and you think of it like I, J, such like this, then you'll notice that it's row, column, right? Yeah, exactly. Yeah, so each of your directed edges, you'll have a head and or a source or destination. There's a head, tail. There's a lot of ways to talk about these, but most certainly that's the case. But yeah, that's a pretty common convention. Wonderful question. I was hoping somebody was going to ask me about that. So I just want to summarize a couple of pros and cons of these types of representations. So if you could represent the graph this way, I just want to mention a couple pros. And I'm also going to mention some cons. And I'm going to put more details about some of the operations you can do on a graph in the notes. So if you want more details beyond this, go just check out the notes. So the big thing that I want to point out, you can view this as a con, but it uses big O of n squared space. You might ask, why is this a con? Well, imagine you have a graph that doesn't have a whole lot of edges in it. Like, say there's only a linear number of edges in terms of the number of vertices, and not necessarily the number of edges. So when I say that, I mean, for example, say some constant amount of vertices, but there's not a whole lot of edges of them with respect to each one. So say I have a whole bunch, I don't have a whole lot of I don't have a whole lot of edges in my graph. Say, for example, it's like a tree. A tree is a good example of what we call a sparse graph. These are ones where they have a linear number of edges, where it's in terms solely of n. So when some people say sparse, usually they mean, they usually mean that the number of edges is big O of n. That's usually what people mean when they say sparse. It's usually around linear in the number of vertices. So if you have a graph like that, is this a very good way of representing it? Well, notice there's going to be a lot of entries that are just going to have nothing in them, right? There's going to be a lot of zeros, for example, there, and a lot of nulls over there. So that's one kind of con about this. A pro about this, because we like our two-dimensional arrays, is if ever I want to check if two vertices are adjacent to one another, they're adjacent to one another, I can do this in constant time. So I could check if two vertices are adjacent or not in constant time. I just look it up, right? I don't have to do any extra work. Another con that I want to point out is if, for example, I want to know all of the edges that are incident on a vertex, that requires me scanning the entire, all of the columns for a given row. So if you're wondering, if I want to get all the, so I want to check or get all incident edges, this takes big O of n time. So it takes linear in the number of vertices, which you can view as a con because, like I said, there might not actually be any in the row, meaning you checked an entire row and you didn't end up finding anything. So that's another con there. One other neat thing is if you ever want to insert or remove an edge. Can somebody think of how I can insert or remove an edge using an adjacency matrix? Yeah, there's a couple different ways we can see how to do this. That's actually one way you can actually approach implementing and representing a graph. It has its benefits sometimes. I think there's different versions. Like there's something called an edge list implementation. There's also a vertex list implementation. But how about this? If I want to insert or remove an edge in the adjacency matrix, what's all I have to do? So if I want to insert an edge into this graph, look at this one at all. Just look only at this one at the moment. Say, for example, I want to introduce an edge from V0 to V2. Well, all I have to do is I just look at the entry, right? And I can flip this from a 0 to a 1. And I can do it same wise also on the opposing side, because I can index those directly, right? Yeah, you just flip a bit. Very simple. So you could do this in constant time. However, I must stress that if you want to insert or delete vertices, that's going to be a problem with this implementation. Why? Because, so for example, if I want to delete vertex 1, there's a couple ways you could approach it, but one standard way is you could literally delete a row and a column, and then you have to shuffle all of the positions over by 1 and all the columns by 1. Sorry, columns by 1, rows by 1. Get my rows and columns mixed up sometimes, but yeah. So you would have to take care of that, and that takes quadratic time, right? So that's one way you can go about it. Some people like to mark rows and columns, but you have to be very careful about that. Now you have to deal with holding extra information, which isn't a part of what I did over here. But yeah, there's a couple other things you can do, and but like I said, these are not the greatest for graphs that are sparse, but they're very good representations for what we call dense graphs. So dense graphs, so these are ones where the number of edges is close to quadratic in the number of vertices. So it's good for this. It's very good for this. Why? Because now you have now you're actually making use of the matrix, right? But yeah, so when we come back next time, what we'll do is we'll look at another way of representing a graph, and then we'll start talking about graph traversals. So that being said, I want to say thank you very much and have yourself a beautiful day. I'll see you later.